All right, welcome calculus students. This is going to be our last example for section 4.1 on antiderivatives. And yesterday in class we were looking at the relationship between position, velocity, and acceleration with the antiderivative. And we finished class yesterday looking at an example where the acceleration was constant. Now, where calculus can really benefit us in physics is when the acceleration is not constant, which is something we didn't look at in the honors physics class because you need calculus to do it. So let's go ahead and look at an example. So for example, let's say that we're given that the acceleration as a function of time of a particle is 6t in units of meters per second squared. And we're also given that the initial velocity at time equals 0 is minus 4 meters per second, and the initial position at time equals 0 is 0 meters. And time is greater or equal to 0 seconds. Okay, so what we want to do is, first thing, part A, is we want to find the equation for velocity and really for instantaneous velocity as a function of time. So using our relationship with the antiderivative, we know that the instantaneous velocity as a function of time is going to be the antiderivative of the acceleration as a function of time. Okay, so this is kind of very similar to solving systems of differential equations, which we did yesterday. So the first thing I'm going to do is I'm going to put in my equation for the acceleration. Oops, that's the wrong thing. What the heck? All right. Oh, here we go. Okay, so I'm going to put in my equation for acceleration, my 6t in here for acceleration. And so I'm going to get velocity of a function of time is equal to the antiderivative of 6t dt. And I can pull the 6 out of that integral. So I get a general solution for my velocity as a function of time, which is going to be 6 times the antiderivative of t, which is t squared over 2, plus our first constant of integration, t1. And then here the 2 goes into the 6 3 times. So I get my velocity as a function of time is equal to 3t squared plus c1. Okay, so now what I want to do is I want to find the particular solution. So I want to now use my initial condition, or my known point, which is velocity at 0 is equal to minus 4 meters per second. Okay, so what I'm going to do is I'm going to put this known point into my general equation. So I know that the velocity is minus 4 when the time is 0. And so therefore, my C1, my constant of integration, is minus 4. So now I have a general equation. Now my general equation becomes my particular solution. So the equation for the velocity is the velocity as a function of time is equal to 3t squared minus 4. And that's going to have units of meters per second. All right, so the next thing we're going to do is part B. And for part B, I want to find the equation for the instantaneous position. X of t. Okay, so I'm using the properties of antiderivatives. Then my position as a function of time is going to be equal to my antiderivative of the velocity as a function of time. So I'm going to take my velocity equation from part A, and I'm going to put it into the integral. So I get the integral of the velocity was 3t squared minus 4 dt. Okay, so I'm going to integrate this, and I get my position as a function of time is going to be 3 times the derivative of t squared, which is t cubed over 3, minus the derivative of 4 dt is minus 4 times t. The integral of minus 4 dt is 4 dt, plus my constant of integration c2. And over here, the 3's cancel. So I get my position as a function of time is going to be equal to t cubed minus 4t plus c2. So now the next step is I want to use my initial condition, or my known point, which is that my initial position is equal to 0 meters. So I'm going to put that into this general equation for position. And so the position is 0 when time is 0. And if I do this, then I get C2 is equal to 0. So now I can write my equation for position, my particular solution, which is x as a function of time is equal to t cubed minus 4t. All right. And so that's how we solve, starting with an acceleration and 2 known points. So I need to have a known point for velocity in order to find the particular solution for the instantaneous velocity. And I also need a known point for position to solve for the instantaneous position. Okay, next is I'm going to do a couple more things with this, some applications that we should already know how to do. So this is kind of a review, but pay attention anyway. Okay, so for part C, what I want to do is I want to find the time or the times when the particle is changing direction. Okay, and if you recall, the particle will change direction when the velocity is 0 and the velocity changes sign across that 0. Okay, so the first thing I'm going to do is I'm going to set my velocity, v of t, which is equal to 3t squared minus 4. And I'm going to set this equal to 0. Because I want to find the zeros for velocity. Alternatively, if you just had position, remember you could take the derivative of position, which is velocity, and set that equal to 0. Okay, so I'm going to solve for t here, and I get my time is going to be equal to plus or minus the square root of 4/3, which is 2 over the square root of 3 seconds. And the negative is not a solution, so I'm going to cross that out. And I know because go back and I look, and you just look at your domain, the domain for time is time has to be greater than 0. Okay, so here, my time, I'm going to go ahead and rationalize this. My time is equal to 2 square root of 3 over 3 seconds. Now, before I box this answer, I need to make sure that the velocity is changing sign across this particular point. Now, this is the only critical point on the position, and so therefore, if the particle is changing position and the velocity is 0, then you're going to have a horizontal tangent line on the graph of position. Which means that it's possible that that's an extrema, but we have to test it. So, I'm just going to kind of do a quick first derivative test. And so here, I'm going to look at my test interval, and I'm going to go from 0 to 2 square root of 3 over 3, and from 2 square root of 3 over 3 to infinity. And then I'm going to do a test value. And again, what I'm doing is I'm testing to make sure that the sign of the velocity is changing across this 0. And so my velocity, which is my first derivative of position, is 3t squared minus 4. That's what I'm testing. So a good test interval in here, 2 square root of 3 over 3. So 2 over square root of 3, if I, what is going on here? Come on. Oh, good, okay. So 2 is 2 divided by square root of 3. Square root of 3 is 1.7, so 2 divided by 1.7 is going to be larger than 1. So I'm going to go ahead and use 1 as my test value here, and then 10 here. So if I put that into my equation for velocity, which is the derivative of position, if I put in a 1, I get a negative value, and if I put in a 10, I get a positive value. So that tells me that that x of t is increasing and then decreasing. So the derivative of x of t, which is the velocity, does change signs. So I can say with confidence that at time t equals 2 square root of 3 over 3 seconds, that the particle is changing direction. All right, part D is I want to find the time intervals, when the particle is moving to the right. Okay, so I know that the particle is going to move to the right if the velocity is greater than 0. So if the velocity is positive, then I know it's going to be moving to the right. Now, we already know that the object or the particle changes direction at 2 square root of 3 over 3. So that's really kind of the critical point on the graph of x of t, and it's also the 0 of velocity. And so if it's going to change direction, then we know it has to be going from left to right or right to left. Okay, so if I go back up and I look at my first derivative test here, using the velocity, not the derivative of velocity, but using the velocity as the derivative, then I can see that ooh, I made a mistake up here. Shoots. All right, so sorry, it's late and I'm tired. All right, so come on. So up here, some of you have probably already caught it, is that the sign is negative and positive. Okay, so that was correct. What was wrong were these two things. So here the function is decreasing and then increasing, and the function being the position. Okay, okay, so we're good. Okay, so anyway, so I know that the object changes direction at this this particular time, and before it, the position is decreasing, which means that the velocity has a negative sign, and after the position is increasing, which means the velocity has a positive sign. So I know that the particle is moving to the right when the time is greater than 2 square root of 3 over 3 seconds. And that's when the velocity is positive. Okay, and then one last thing is I want to, part E, is I want to find the speed, or find, let's do this. Okay, so for part E, is the speed of the particle increasing or decreasing at time equals 1.0 seconds. Okay, so I know that the speed of a particle is increasing if the sign of the velocity and the acceleration are the same, so positive, positive, or negative, negative. And I know that the speed of a particle is decreasing, which means it's slowing down, if the signs of acceleration and velocity are opposite. So what I'm going to have to do is I'm going to have to check the signs of the velocity and the acceleration at time equals 1 second. So I know that the equation for velocity, v as a function of time, is 3t squared minus 4. So v of 1 at 1 second is going to be 3 times 1 squared minus 4, which is less than 0. Remember, I only care about the signs for this question. And then the acceleration is given in the original problem statement is 6t. And so the acceleration at 1 second is 6 times 1. And that's greater than 0, so it's positive. So therefore, since the signs are different, I can conclude that the speed is decreasing at t equals 1 second. Okay, so that's the last example for 4.1. So you are armed and ready for the homework that is due on Friday. So, so this video is only, let's see, about 15 minutes, a little bit over 15 minutes. So you should have plenty of time to get started on the homework that is due on Friday. So I encourage you to work together, but make sure you work and get quite a bit of it done. And then we're going to actually skip ahead to 4.3 tomorrow, and we'll go back to 4.2. So if you want to look over section 4.3 before Wednesday's class, that would be cool. All right, have a great rest of the day, and I shall see you tomorrow.